Well, we're going to begin our look at the subject that was written by, and my pronunciation is always wrong on this, Muhammad ibn Musa al-Khwarizmi. Khwarizmi. I apologize if my Arabic's off. And his book, the Compendous Book on Calculation by Completion and Balancing, otherwise known as Algebra. And completion and balancing is actually the clue. And so we're looking at 800 common error technology of human beings that we get to learn now. And so what we're going to focus on is the idea that we can represent quantity in a letter, or as we're going to say, a variable. And so these are called variables because they can vary. And if you watch the video, the reason we ended up with X is the sentence that it came out of was a translation for the unknown thing. And so we can hold in our mind that when we see variables inside of algebraic expressions, those expressions work. They do the work that they need to do to move us through the quantity, but they're going to take the place for the unknown thing. And so we're going to have a grammar that we put around these unknown things. And that grammar is going to focus on parts. And the first parts that we get are expressions. And so expressions have variables in them and numbers. Let me get to my definition if you hear me clicking on there. This microphone's a little bit lighter than the other microphone I've been using. I'm trying to deal with this fan noise problem here, so I've been trying some different microphones. If you have to jack up the volume, my apologies. I have it a little cranked on this side. I'm not sure that's helping on all parts here. But let me move over and let's see if we can see this here. And so we're going to look at expressions first. And so an expression, an algebraic expression, an expression in general contains any form of number, a variable, and operations. And so we studied different sets of numbers we could use, and we've studied operations. We can take things to powers, we can take roots of things, we can multiply, divide, add, and subtract. Those are our operations. And then we also have our different sets of numbers. And then variables are our new things where we'll let a letter take the place of a number. And so this is an expression that says I have 3 times an unknown quantity to the second power. And so these expressions are like little statements within our mathematics. And we string them together to get more done with them. And what we can do is we can evaluate expressions. What the expression does is, I'm going to scroll down here, it holds a place for unknown things until we know what they are. And there are many ways we can find out what they are. So let's look at some expressions and what we can do with them. So I'm going to use an example from the book. 7 plus 5 times, in parentheses, another quantity, x minus 4 cubed. And right now, I can't tell you what this is. because of this unknown quantity in here, this expression has an unknown value. But if I were to say if x equals 6, well, now this does a really nice thing, and we'll look more and more into what the equal sign does, but it tells me wherever I see this, I can put this. And it also tells me the opposite, too. Wherever I see 6, I could put in x. We tend to think left to right with equations. We'll learn to think in both directions and make sure that we can see something on one side is equal to something on the other. Sometimes we might not be able to get the variable itself, but we might, let's say we knew what x minus 4 was. Right? I could say x minus 4 is equal to 10, and now every time, not 10, x minus 4 is equal to 2. Sorry, so I want to say. Minus 4, and now whenever I see x minus 4, I could put 2 in, and since I see x minus 4, I can put 2 in. So when we see equations as we come along, we'll realize that they're flexible things. But for right now, for our expressions, this is saying, I don't know what to do with this unless I know what part of it is. There's something that tells me what x is. And so I want to, hey, x is 6. So I can rewrite this. Now, I always use extra parentheses whenever I see my variable. I put it in parentheses. That way, if there's any powers or anything, I can take care of it. And now we're going to use order of operations. And I've been talking about order of operations on and off as we talked about powers and bases. I've brought them back up. And so we do parentheses and grouping symbols first, exponents and roots, multiplication and division, addition and subtraction, and we go left to right. So I have this grouping symbol to do first. So 7 plus 5, 6 minus 4 is 2 cubed. And I've simplified the expression one level, and I've done my grouping symbols. Now I come through and I do all my powers. And so I have 2 to the third, which is 8. And I've done all my powers, so I come back down and do my multiplication. And I get 47 as what this expression is if x is 6. And that if x is 6 is really, really, really important. Because, hey, I could come back in and I could say, you know what? What is it if, I could take that whole expression, could be using the same expression, and you say, well, if x was negative 6, we'll do its opposite. Now notice, the power of the expression comes in here. I haven't needed to rewrite any of this. And if we do our jobs well, this represents something of reality for us, and this represents something else we measure. And so I can make a general statement that will apply for many cases, and then when each case comes up, I can get a particular answer. That's what having an unknown quantity does for us. So in the first case, I went through and I worked out if x was 6, this expression would give me 47. But what happens if x is negative 6? Well, I go through the same process, and I'll use my parentheses. Cubed. Right. And so now do my order of operations. So negative 6 minus 4 is negative 10. And negative 10 cubed is negative 1,000. And negative 1,000 times 5 is minus 5,000. And so 4,993. Huge difference in output. But this itself, this expression, is portable. And it lets us vary the variable, which is what its job is. It's there to help us use different things that can represent an unknown quantity. And unknown quantities happen a lot. We might understand a rule for something happens, but we don't have the measurements that make the rules come through. Or we might have the rule in place, and we need to use it at different occasions so that different measurements come through. Let's look at another expression to evaluate here. I'm going to do a lot more examples in this unit because I think examples help. So let's see, x squared plus 5x minus 3. That's what I'm going to look at next. I'll come down here. X squared plus 5x minus 3. Now, again, this has no value. But if I could say, hey, if x equals -6, what does this become? Now, wherever I see x, I replace with -6. Now, in this case, I have x repeated more than once. So -6 squared, 5 times -6, minus 3. So 36 minus 30, minus 3. So I'm going to do my power first, and a negative squared is positive. Do my multiplication, 5 times -6 is -30. So I get 6 minus 3, or 3. And so we're seeing how expressions can be evaluated. Well, in both of these cases, I only had one variable, but I can have many variables. Multivariate functions come up a lot. There might be many things we can measure. So let's see, minus 2x squared minus, or plus 5xy minus y cubed. And so notice, in this case, there's two variables. There's x and y. And I could come through and say, well, you know, what would this be if x was 4? If x equals 4. Well, it's not going to give me a full answer. I could simplify it, and I could get things that were numbers, but I would still have this variable in y. So to evaluate this expression fully, to get a solitary number out of it, I also need to have a value for y. And so now wherever I see x, I can put in 4, and wherever I see y, I can put in -2. So again, I'm going to use my parentheses, that way I can keep track of powers and hold signs. And now I've substituted in these values into the variable appropriately, and I can evaluate this expression. So let's go through and do all my powers first. That's a squiggle up there. That's not a power. I'll make that squiggle squiggly. That's the actual power. And so doing my powers first, I have 16 times -2 plus 5 times 4 times -2 minus -2 cubed is -8. So now I'll do my multiplications. -2 times 16 is -32. 5 times 4 is 20. And 20 times 2 is -40. And a negative times a negative is positive. And so now I get -72 plus 8, or -64. And so the number of variables can be multiple in expressions. In fact, this leads to one of our first things that we can do. We can make something called a formula. And a formula is an expression that represents a model of reality. And it has numerical rules that take in measured inputs and it outputs a result which is measurable. All right, let's oops, 2 seconds here. All right, right, so let's move this over here. And I think formulas are how a lot of us interact with mathematics. So the example in the book shows a model of exercise ratios with different types of activities, and then it also looks at a weight type model exercise in graphs. So I'm going to open kind of both of these. And so, for example, they look at a heart rate if you're exercising while sitting. Exercising while sitting. They say it's the couch potato model, right? On it, couch potato exercise, which there are things you can do while watching TV, lifting weights, small cardio, with strength training, which I think is what their picture example shows, except the person's eating, and where the heart rate is on it. So H is going to be our variable for heart rate, and then we have 1/2 or 1/5 220 minus A. 220 minus A. And so with formulas, you need to know what everything is. And so H is the heart rate in beats per minute, and the A is the your age in years. And so this finds an example of what your heart rate should be based off of your age. So you have a measurable value, the age of a person, and then you have a predictor there, and I think this is peak heart rate. I think it would be peak heart rate. Now they compare that, right? This is the couch potato formula. They compare that to a formula for heavy exercise, where the heart rate is 9/10, 220 minus A. And if we kind of look at these formulas, these parts are the same. This age factor, right, brings up or down the heart rate. And then in this multiplier is based off of, and this is, they say work it, right, which is, this is heavy exercise. This multiplier is based off of the exercise being done. And so these models make a predictor based off of things you can measure. In fact, they go further on in mathematical models that you can look at graphs and use graphs to help make predictors. And one of the things, let me see if I can get my picture to shine in on this here, that we do with graphs. Come over. Where'd you go? Come on, guys, you're hiding from me here. Let's see. There we go. There's the graph. If we notice, the shape of this graph is curved. And curved graphs tend to be quadratic or to squared. And so they're able to put a formula here by matching the shape of the graph to known functions. And that's part of what we learn in mathematics, are the different types of functions we can use that will shape our graphs. So we're going to look at this graph here, and we come up with this function that is the mathematical model for the exercise needed per day, or the number of calories needed by women in an age group with moderately active lifestyles. And so it makes this graph, and that graph can be represented by these numbers. In fact, let me see if I can pull up my web browser here. I get to the web browser. I think it's on the same thing. Hold on. Yep, it's on the same page. But I'm going to change it to a graphing calculator called Desmos.com. Let me come over here. Desmos.com. It'd help if I could type, not .co. Not having a good typing day. There we go. Then I'll open up Desmos, and I will put in the formula. I'll do it using x. So let's see, the formula that they had, that's on the next page here, is negative 66x squared plus 526x. So I'll come over here, negative 66x squared. And notice how squared things make a parabola. And then we were to plus 526x. And then what am I going to change here? Plus 1030. And I want to zoom out a bit. So minus sign out. We've got a really steep parabola here. In fact, I think the thing to really focus on is this upper part of the parabola, because all the calories are in the 2000 range. Let me get by the 2000s here. Start seeing, yep. So now I'm going to, plus in, and scroll up. And so we can start seeing the shape here. And if I were to get the size of this graph to sit over the bar graph, I would see that this upper chunk of it matches that curve we saw. And when we see curves, we tend to see squares in our problems. All right, so and that's what mathematical model does, is we look for similar patterns in our data that we have equations or formulas for, and we adapt our equations and formulas to work with that. And yeah, that's right, they used odd grouping numbers for this. They used the grouping number in place of x instead of an age number. All right, so let's look at what makes an expression in a formula. The bits and pieces that go into making an expression and a formula. So we know that we can use these things to describe things in reality. We have them coming across. So we want to look at the pieces that these are made of. And so the parts of an algebraic expression that are separated by additions or subtractions are called terms. And so if I have an expression, make this one y. Right. This is a term, this is a term, and this is a term, because each one of these is separated by an addition or subtraction. And again, I will repeat with PEMDAS that addition really is the same as subtraction. So I could say they're separated by additions. Then in the thing out front, it's called the coefficient. It's the multiplier of the variables if they exist, right? Because you don't need to have a variable, right? We can kind of think this is 1 if we're thinking of it as having a variable, or it's just a number on its own. Sometimes that'll get the term constant. It's a constant term because it doesn't change. And so one of the things we can do is we can look for things called like terms. So if I have 3x minus 7y plus 3 plus 5x, these terms are called like terms because it has the same variable to the same power. And with like terms, I can bring them together. It's like saying I have 3 x's and 5 x's, so altogether I have 8 x's. And collecting like terms is part of simplifying expressions. or a thing we would do called simplifying the expressions. We can also take a term and factor it. And so I could have 3x times 4y and 12z. And these are all factors. After I put the numbers together, I get, 144 x, y, z, and these are variable factors. Variable factors. All right, what I'm going to do is I'm going to look at the properties of real numbers and complex numbers that we had and how they work with expressions. So I'm going to rewrite the properties of real numbers again. And I'm going to skip the closures, and I'm going to focus specifically. Remember, we had some for additions and multiplications. And so we had commutation, a plus b equals b plus a, and a times b equals b times a. They were associative, a plus b plus c equals a plus b plus c. A times b times c equals ab times c. There was a distributive property, which was a times b plus c is equal to ab plus ac. And we will always want to remember our identities, which is a plus 0 equals a, and a times 1 equals a, because we'll find creative ways to write these things to help us with our expressions. So let's use a couple of these. So remember how I said we could add or subtract like terms? If I have like terms, well, that's like the distributive property. Notice there's the same thing here, and I can pull it out front. Pull it out front. There's the same thing here. I can pull it out front. Well, I'll pull it to the back because it's commutative. Doesn't matter the order I multiply. And 3 plus 7 is 10. And so collecting like terms is directly linked to this property of real numbers. So even though we're calling it something different and we're making a technique out of it, that technique is a property of real numbers. And it doesn't matter that I don't know what this number is yet. It's still a number. I just haven't found a value for it. And so this is called simplifying algebraic expressions. Let's simplify a few algebraic expressions. Let's simplify 5 times 3x minus 7 minus 6x. So 5 times 3x minus 7 minus 6x. So, order of operations would say, do this first, but I can't. I have this unknown thing. But I have a distribution that I can do where I can multiply this to each of the terms in it to simplify the answer. So 5 times 3 is 15x minus 35 minus 6x. And now I can use my commutative rules to get my x's together. And so, or I could say I'm collecting like terms. So 15x minus 6x is 9x minus 35. And this is a simpler form to write this in. And one of the things we mean by simpler forms is I have to replace the variable the least amount of times. I've simplified it to the variables once. Sometimes we simplify it the variables more than once, but it's the least amount of times. We can't make it any smaller. It has the least amount of terms. So when we go to calculate we have less places to mess up, or at least that's how I think of that. Jeff's going to mess up his signs somewhere. You know, how can we make the least amount of errors? All right, let's look at another one here. This one's a little bit trickier. So I'll take my time writing it here. I have 2x squared plus 4x. 6 times 2x squared plus 4x plus 10 4x squared plus 3x. 10 4x squared plus 3x. So again, I don't know what x is, but I do have these places I can distribute. So I'll start by distributing so that I have nothing in parentheses anymore. Right? One of the things the distribution rule did was get rid of parentheses, and that'll help me here. So 12x squared plus 24x plus 40x squared plus 30x. And now I have x squareds and x's. So I'll bring the x squareds together, and I get 52x squareds and 54x's. And I have simplified it. Something that happens quite often, and I'll do this one, is a negative sign outside of a parenthesis. And so if I have a negative sign outside of a parenthesis, we can think of this as -1 times the parenthesis. And so I can distribute it in. It distributes in this negative. So even if I'm subtracting this quantity here, we can think of it as like a negative. And that goes back to the definition of subtraction, which is a minus b is the same as a plus negative b. If I have some negative outside of something in parentheses, I can distribute it for. Let's look at one of those. See here, 8x plus 2. Here. Get my last big one here. So 8x plus 2. 5 minus x minus 3. Alright, so I want to start inside these parentheses, and I want to start peeling away parentheses, kind of like a reverse onion. And so I'm going to distribute this negative into each term. So this becomes 5 minus x plus 3. Then I'm going to have my 2 outside. And I've got two options here. I can collect like terms and then distribute the 2. Or I can do the distribution first. Doesn't matter, I'm going to get the same answer. I'm going to collect like terms. So 5 minus x plus 3, so that's 8 minus x, 2 outside. And then I'm going to have 8x, now I'm going to distribute this 2. Plus 16 minus 2x, or 6x plus 16. And these are examples of simplifying expressions. And again, simplifying helps us put these things in a better order to process. All right, this is kind of section 1 in algebra. We're getting in, we're looking at our expressions, we're manipulating our expressions, and we're working on getting these to a better place. Until again.